We're going to talk a little bit about chemistry and thermodynamics, and then get into cryogenic containers, smallest to largest, and kind of just review how cryogenic containers are made and why they're made that way. Because it really doesn't matter how big or small the container is, they're all made the same way with the same concepts, right? We're going to talk about application, supply chain, and also get into what Rego sells. Cryogenics, it's basically, it's the production of cold is what it means, right? So anytime you hear a cryogen or cryogenics, just think cold. It is an engineered discipline that deals with the production of it and also low temperature. So to get a cryogenic in a liquid state, you got to be minus 230, 240 degrees Fahrenheit. So it's really cold. So cryogenics, what's a cryogen? Where does it come from? It's the air that we're currently breathing. 78% is nitrogen, 21% is oxygen. The remaining balance is all kinds of other stuff that's hard to get to if you're trying to liquefy it. I put in an extra bullet point there for helium, hydrogen, CO2, methane, and LNG because those are liquefied in different fashions. So I'm primarily just concentrating on nitrogen, oxygen, and argon. So that's where we get the cryogenics from. And here's the chemistry part. Matter exists in 4 different phases or stages: solid, liquid, gas, gaseous, or plasma. We're only going to talk about liquid and gas today, just those two, because those are the only two that apply to what we're discussing. If you look at liquid oxygen, this is the temperature at which the product goes from a gas and turns into a liquid. So for liquid oxygen at certain pressures, the temperature of that gas to go to a liquid, or its boiling point, it's got to be minus 297 degrees Fahrenheit. Argon's 303, nitrogen's 320, and hydrogen and helium are really cold. So why do we liquefy it? Here's several reasons. The economics of it and the transportation of it. It's really easy to transport these products in a liquid state.
The reason we use the cryogenic cylinder is because the cryogenics is in a liquid state. And if you look on the picture on the left, that's a liquid cylinder, and that equals 12 to 16 or 16 to 20 high pressure gaseous cylinders. It's much more economical to liquefy product in a liquid cylinder than it is in a gaseous cylinder, depending on the application and how it's used. Now we're going to talk about cryogenic containers and how they're made. Basically, just think of a thermos bottle, a bottle within a bottle. So we're going to talk a little bit about thermodynamics, which is an educated way of saying heat transfer. And basically, when making a cryogenic container, no matter how the size, it's good to know a couple of rules about heat transfer, and that hot always flows to cold. So examples of that are, when you're outside and you feel the sun heating on you, the heat from the sun is warming you up. Or if you're in front of a fireplace, the warmth goes towards the cold. Cold does not leave your body and go to the flame. So just remember, heat's always trying to get to the cold. And the third example there is if you were to put an ice cube in your hand, the heat from your body or your hand is what's being transferred and making that ice cube melt. So when it comes to heat transfer, there are 3 types: conduction, convection, and radiation. And we're going to talk about all 3 of those next. So conduction. A simple example of that is if you have a hot cup of cocoa or coffee and you place a silver spoon in it, the metal of the silver spoon is capturing the heat from the hot coffee, and the heat is going up or conducting. It's a conductor of the heat, so it's transferring that heat up. A plastic spoon will have it, but it's not as good as a thermal conductor, so it's not going to be as good as metal. Another example is a fireplace poker. If you poke the fire with the poker and you were to keep it on the flame, that heat from the flame is eventually going to travel up that poker and cause it to get hotter and hotter closer to your hand as you're holding it. Another example of conduction heat transfer is the hot steam coming off a cup of coffee, or if you have a boiling pot, the steam that's coming off is you're transferring the heat from the liquid to a gaseous state. So the next two, heat transfer, is convection, which is basically you have something that's causing the heat to be transferred from one place to the other. So a good example of that is a hair dryer. Hair dryer gets turned on. The convection of the heat transfer is actually transferring it, or it's a driving force that causes the heat to go to a specific place. It's also like the desert wind blowing against your skin. Again, the heat is seeking out the cold. And then the third and final version of heat transfer is radiation, which is basically from the sun. And that's how we get sunburn, X-rays, and gamma rays that come from radiation. There's not a whole lot we can do about that, but there are some tricks that we have, materials of construction that can eliminate that heat transfer as we make a cryogenic container. So this is a example of a cryogenic container. It's basically a thermos bottle. So you have a bottle within a bottle, and the space that's in between those two bottles is called an annular space. That annular space is going to have a pulled vacuum, and it's also going to have super insulation. And that's going to create a barrier that's going to help stop that radiation from getting to the cold liquid that's in the middle bottle. So the middle bottle that you see that's where the molecules or the cryogen is going to be located, liquid nitrogen, oxygen, or argon, and others. And then you're going to have a vacuum space or a barrier that's going to stop certain heat transfers or thermodynamics from getting in there to warm up that cold liquid. And because our main goal with a cryogenic container is to keep it in a liquid state for as long as possible. The other points here are the materials of construction, meaning the inner bottle and the outer bottle are going to be made out of different materials of either steel or stainless steel, depending on which molecules we're trying to keep cold. So big difference between a hydrogen container and a nitrogen container. Nitrogen's at minus 320. Hydrogen in a liquid state is at minus 450. Those are going to be made with different materials, different types of stainless steel for the inner vessel, and different types of carbon steel for the outer vessel. Again, the key here is to try and eliminate as much heat transfer as possible into the inner container. And then you see these little 4 redded connections, the long heat path, the red little joints there, that's connecting the outer vessel with the inner vessel. You want to make sure those are as short as possible. And again, they're using the right materials of construction, so it's reducing as much heat that gets in there. You're never going to 100% eliminate heat from getting into that inner vessel, but if you design it correctly, if you use the correct material of construction, then all of those 3 things together will help try and keep that liquid as cold as possible for as long as possible, which is the goal. So when I mentioned super insulation, in the olden days, they used to use perlite, which are really, really fine white pellets. And basically with super insulation, it's a mylar wrap. It kind of looks like aluminum foil and paper. And you're just wrapping the inner vessel around. And again, this is in the annular space where the vacuum will get pulled. And the combination of that vacuum and this super insulation will help keep radiation out of the inner vessel. So here's an actual picture of a big nitrogen or hydrogen trailer. The super insulation, that's the inner vessel, and they've used super insulation to wrap that inner vessel. That and the vacuum would be the 2 things in the annular space that would help create that barrier to try and keep the radiation heat transfer out and try to keep the cold liquid that's inside as cold as possible. So super insulation plus vacuum equals that thermal performance. So when pulling a vacuum on that annular space, basically what you're doing is it's paper and mylar. Again, the mylar kind of looks like aluminum foil, but it's not. Everybody has different ways of wrapping it and how many times they wrap it, and there really is a big science to it. You want to take your time and wrap it because you also want to make sure you don't tear any of the super insulation, because anytime you have a tear, you have a break in the barrier, and that's an opportunity for heat to get in. Once you've wrapped it completely, you're going to pull a vacuum, and when you pull the vacuum, you're basically heating up that inner vessel 300 plus degrees, and you're pulling all the molecules out of that annular space. So this is what it looks like from a side angle. The warm natural environment, that is the outer wall, and the where the number 3 ball is at, that's the inner wall where the cryogen or where the liquid was stored. So as you can tell, what happens is when you pull that vacuum, you're trying to pull as many air molecules out of that spacing, and you're creating a solid barrier to prevent heat from going in there. But as I mentioned before, you cannot prevent heat from getting in there. You can only slow it down. So by pulling that vacuum, there will be very, very slow moving molecules that are cold. They hit the outer wall of the outer vessel, and then it's going to bounce to the inner wall, and it's going to transfer that heat with it. So that's just a visual of the molecules bouncing around in that annular space. And then the last thing on this is on the container itself. If you know you've made a good container, if the nominal or normal evaporation rate, which is also called an NER, that is basically a way of it's a rate in which the liquid turns from a liquid into a gas. So basically, if you make a really, really good cryogenic container, you're keeping the liquid as liquid for as long as possible. And the evaporation rate, or NER, is how many pounds per day of product actually evaporates from a gas to a liquid. And when you have a cryogenic container, if it's boiling, if the liquid's boiling too fast and it's turning into a gas, it's going to create higher pressure, and that product's going to vent off, which means you're losing that product. So the better the container you make, the less product you lose. So the amount of product loss from venting is what you're trying to control. And again, as I mentioned, it's basically NER is expressed in pounds or percentage of product lost per day.
So that's a picture of a liquid cylinder. You can get a lot of gas out of that, and you're saving space. And overall, it's probably cheaper for rentals because you pay a rental on the piece of equipment, and you pay a product price as well. So that's just what they look like. I'm going to get into a couple of functions of the cryogenic container itself. On liquid cylinders themselves, and the other containers don't, but the inner vessel is going to have it acts as a vaporizer. So it's a little coil that goes around the outside of the inner vessel. And that's useful because it's going to, if it has to, it's going to take liquid and turn it into a gas. So anytime you hear the word vaporizer, all the vaporizer means is you're taking some form of liquid and converting it to a gas. You're just changing the state of that product. And so a vaporizer is built into a liquid cylinder. All the other cryogenic containers, because they're so much bigger, the vaporizer is going to be a separate unit outside of the container. So in this particular case, how would you do pressure transfer fill, or how would you fill a liquid cylinder? Basically, all you need to know is you connect it to the liquid line, and whatever source is filling the container has to be at a higher pressure than what the pressure is that is receiving it. So it's all about pressure, and that's a pressure transfer. So you're going to have a liquid line that goes in, and you can use the same line to go out, and then you have a gas line as well. If you ever have to drain or take the liquid out, very seldom you do with a liquid cylinder because it's not a lot of liquid and you usually just vent it. But if you have a bulk tank, like the 6,000 gallon bulk tank outside, and all of a sudden there's a valve that goes bad and you got to drain that tank to fix the valve, you then have to pull that liquid out, which means the pressure in the container has to be higher to receive it. So Wherever the liquid wants to go, the source that's pushing, it has to push the liquid out. It's got to be at a higher pressure. Every cryogenic container is going to have a pressure builder. What that means is, and in this particular case, so you've got liquid here. This is the head space on the inner vessel. As this liquid bubbles and turns from a liquid to a gas, it increases the pressure in the head space in here. What happens is, let's say there's a welder downstream who's using it as a gas because he's welding something, right? And he's working really hard. Well, he's starting to suck this dry. He's starting to use all the gas from this, and the pressure starts to drop. Well, what happens is you pull liquid from the bottom. It goes through the vaporizers. Again, that's connected to the inner vessel, and then that cold gas gets dumped into this headspace. That increases the pressure of the headspace. So the pressure builder is an internal function that helps to keep the pressure of the container at the pressures that is needed so whoever's using it can keep working. Here's my other example. Got a welder, he closes up on Friday, turns everything off, comes back to work on Monday. As this liquid cylinder sits, heat's getting in there. It's been sitting for 2 days, right? It's going to build up pressure in that headspace. He then goes to use it. What the economizer feature does, it pulls from the higher pressure here first. And then once that pressure gets, depending on where it's set, once all that high pressure, all the gaseous pressure that can be used for his functionality, then the pressure builder kicks on. So the economizer basically is saving a lot of money, and it helps them to retain as much of the product as possible. Before economizers were used, the guy would have to come in, turn on the vent valve, and just blow it down to the pressure he needed. So he's wasting product. The economizer is multi-function, where it actually helps to optimize and take advantage of that higher pressure and pull from that headspace first, and then the pressure builder will kick on. And it's all based on your settings. So this is a quick side view of a liquid cylinder. At the very top is all the hardware, and that's everything that Rego sells. You got a gas withdrawal line. You've got, this is just a side diagram to show you what the inners look like, where the soldered vaporizers go around. A liquid cylinder is going to have a liquid level gauge. The pressure builder is always at the bottom of the tank because it's going to pull the liquid through gravity to pull the liquid and have it go through the vaporizer to change it to a gas. You have a liquid withdrawal line, and then you got the vacuum space or the annular space in between the two. On liquid cylinders, you know, the space in between the outer and the inner is, again, it goes back to the design. You know, the more space you have, the worse that barrier is going to be. So they try to design it so it's very, very tight. And the challenge with the nesting of putting the inner vessel into the outer vessel, you can't scratch or tear any of that super insulation when you're nesting it, because if you do that, then that becomes a huge heat source. And a lot of times, I've seen bulk tanks where they've built them, they've accidentally cut it, and then they fill it, and you can right away see they got to undo it, right, and rewrap it and start over again. So there's a science to that, and especially with trailers, because the two bottles are so big, the two different tanks are so big and long, it literally take a whole shift to get a trailer inner vessel nested into an outer vessel, because you just got to go really, really slow. This is the hardware on top of a liquid cylinder. This is the Rego. We identified the Rego number series in the description for you as to what Rego parts go where. Micro bulk. This was I'm going to say in the late 90s, Chart came out with a micro bulk truck, and it was a small delivery truck for the independents to be able to reduce their cost to go, and if they happen to live close to an air separation plant where the liquid's made, they could go pick up the product. And a picked up product price is a lot cheaper than a delivered one. Those were originally the 1000 and the 2500, and then they just supersized a liquid cylinder into a microbulk. Everybody sells microbulks now, and microbulks have gotten huge. Liquid cylinders and microbulk, the unit of measure is always going to be in liters. So if it's silver looking, it's in liters. Once you get into bulk tanks and bigger, it now goes to gallons. The other thing on a microbulk, see how the microbulk is on like a little base or a stand? It's really super easy to take a forklift, depending on the size, empty, pick it up and place it somewhere. And now you've reduced a lot of civil work, and it's all you have to do is have a flat area, and now you can plant that bad boy anywhere. And usually there's a vaporizer on the side of it as well. So it's not only the cryogenic container, but it has the vaporizer, and it's self-sufficient. But now it's easy to move around. But you got to move it empty. You can't move it full for the weight perspective. So it's all about the molecules. How much of the nitrogen can I sell to you? Because that's where the cash is. That's where the margin's at. And that's why, you know, when there's a quality issue or a valve goes bad, yeah, it's a $200 valve, but the reality is the molecules aren't being sold. So that's why people get upset very quickly. So microbulks, again, it's here's a quick all the different valves that go on a microbulk and where they're located. And it's basically a mini version of a bulk tank is what it amounts to. It's just a larger size liquid cylinder. These are the Rego valves and the type, you know, where they would be and what they are and where they go on it. Just a larger version of a liquid cylinder, and they've gotten so big they're now competing with bulk tanks. So those are just pictures of bulk tanks if you haven't seen one. So this is a standard bulk tank setup. Again, the bulk tank itself it's just a big cryogenic container. Downstream of that is going to be a vaporizer. A vaporizer, again, just changes the state of the molecule from a liquid to a gas. And I got some additional slides after this on how a vaporizer works. And then downstream of the vaporizer will be a final line assembly, and then it goes to the house line. Typically what the majors do in some large regional independents, when they're dealing with their customers, they're responsible for all that equipment on the pad until it touches the house line. So if anything goes wrong with any of this, they have to come out and do the maintenance on it. Depending on the size tank will determine what, again, all that equipment will have a monthly fee for the customer, and then there'll be another product fee, and the product is usually priced per 100 standard cubic foot. So for every 100 standard cubic feet you use, there's a price outline for it. When it goes to the house line, this cryogenic system and how it's set up, the biggest thing is flow rate. What is the customer's end user's flow rate? What pressure do they need? And temperature do they need? And those are the three things the final line assembly kind of regulates for you. And then from wherever the tank is located outside, you also have to factor in the distance of all the piping and where the product's actually being used. The key, you gotta size the vaporizer correctly based on the flow rate and the pressure and the temperature. It's mainly the flow rate. So this is a bulk tank. The thing with a bulk tank, it's got a bottom fill and a top fill. Because of the size of the inner container, and because the customer may still be using product, like for instance, the 6,000 gallon tank out there, the house line I think was at 150 PSI. If he were to come make a delivery today, the driver has to make sure that the house line pressure stays at 150, and then he controls the liquid coming in the bottom. If he comes in and delivers that whole thing in the bottom, he's going to create more pressure in that headspace. So the top fill allows the liquid to splash down and fill it from the top. When you fill it from the top, you're collapsing that, you're turning a lot of that gaseous headspace into liquid, which means you're lowering the pressure. So the driver's manipulating a top fill and a bottom fill to make sure he's maintaining what pressures are needed. during the time of the fill. So a lot of times, industrial gas companies or whomever will make a delivery and the customer won't even know they're out there. And then they just drop off an invoice somewhere, or mail. There's usually a mailbox in the fenced-in area, and at the end of the month they just pay the bill. And that's part of charts with the micro bulk was you're now turning your cryogenic usage into a utility. It's like turning on and off a light. It's always here. You never have to worry about it, right? But from their perspective, depending on who the customer is, they could make as many deliveries as they wanted to it. Because the more they deliver, the more money they make. And then these are the Rego products category of family of products and what they are and where they go. That just gives you a picture of them. And then this was, I think it was based on the size of the bulk tank itself, helps determine the size of the proper valve that goes on it and the differences between the two. So like I said before, like on a bulk tank, 1,500 gallon up to 13,000 gallon are standardized. And the reason they're standardized is because of the shape of the heads. They get pre-made heads, and the same head is used, I think, for like a 15 and a 3 and maybe a 6. And then a different size heads used for the 9, 11, and 13. And all it is the tank just takes a different shape, right? But the manufacturers are saving money by standardizing those heads. Mm-hmm. A lot of them make what they call engineered bulk tanks, which is basically a non-standard or a tank that's bigger. So 20,000 gallon, 50,000 gallon, and Acme used to do tank repairs as well, and the people who do tank repairs today they're one of their advantages. They'll do the tank repair. They got vaporizers set up with somebody. They do the final assembly. They can sell it as a bundle and package it all together, which makes customers happier. Those are our products by number series that get used where. Talk a little bit about vaporizers. So you see how that vaporizer is shaped? It's a star fin shape. You see the tube in the middle of it? So I just want to remember we talked about heat transfer. The liquid product stays in the inner tube right down the middle, right? So all of the way this is designed is this is the right material to absorb heat. So the heat just gets captured in these fins, and as the liquid is running inside the tube, it's getting warmed up and changing from a liquid to a gas. And that's called an ambient vaporizer, meaning ambient, it's just the sun hitting it, and there's no external force helping it. And the biggest thing with the vaporizers is sizing them correctly based on someone's flow rate. Because it determines how tall the vapes are, how many you need. Because you always want to make sure you have more than enough vaporizer, because you always want to make sure the customer's in the proper supply with the right pressure and the right flow rate. Sexy has ambient vaporizers, plus they do a lot of non-standard vaporizers, and such as something like this, where you could have like a trim heater vaporizer. You have an external source where it's being electronically heated. So all of a sudden now you have if you're heating it through electricity, the vaporizer warming it up, then all of a sudden you can reduce your footprint. And it becomes, it just depends on how elaborate they want to get, and what they're trying to accomplish will determine how to properly size that vaporizer. Now I'm going to get to transports. This is an 8,400 gallon nitrogen transport. And the biggest thing with the trailers is the nitrogen and argon trailer specific, well, almost all trailers. The engineers who design these, and they want to know what the weight is of everything that's on there. So DOT laws says that that trailer with the tractor, with the driver, all of it with the payload, meaning product in it, has to be 80,000 pounds or less. If you're over that, you're going to get a ticket. So what happens is, and this became a 15, 20 years ago, the Air Liquides, the people who were buying the trailers, all of a sudden started putting weight penalties into the trailer manufacturers because it affects their payload, right? So if you can make that trailer, they use an assumption on the driver's weight and the tractor, and then a lot of times they'll take it and weigh it completely empty right when it's new to find out how much it weighs, and then you do a quick calculation that determines how much product they can put in there. The more product they can put in there, the more cashola they can make on their side. So it's very important to them to be within weight. So what a lot of customers did is they put a weight penalty in there and said you have to, if it's 80,000 pounds in total, just using it as an example, let's say it's 40,000 gallons of product, then everything else has to be 40,000 gallons. If you came in at 40,200, you paid a penalty, or you had to reduce your price X amount because the weight is that important. USA is DOT law is 80,000 pounds over the road. In Canada, it's like 120,000 pounds. So whenever the trailer manufacturers make something for Canada, they're a lot bigger in size. That's a 17,600 gallon hydrogen trailer that goes to Canada, and that can only be used in Canada. It can't be used in the United States because with the tractor and with it weighs too much. Nitrogen and argons are made the same. For the most part, have the same design, a lot of similarities. Oxygens are going to be the same design but made with different materials to handle the oxygen. The hydrogen trailers are a completely different animal. LNG trailers are made quite a bit from the same manufacturers for Loxlin and Lar. This just gives you an idea of sizes. And then these are all the functionalities and valves that go on a trailer. It's kind of this is the back of the trailer. And everybody has a different complete design in the doghouse. Realistically today, there's probably 200 to 300 trailers get quoted a year, but ones that are actually bought, and when I say that, that's Loxlin, Lar, nitrogen, oxygen, argon only. There's probably 75 to 150 that actually get bought. And then these are all of our products that would potentially go on a trailer as long as the weight's good. And the trailer people with the industrial gas companies are extremely niche, and them more than anybody else, they don't like changing stuff. They're set in their ways. And then we got pictures there, and then I guess depending on the size, again, depends on the size of the trailer. And basically that comes down to flow rate, what size valve works best. So now going to get into ASUs, or air separation plants. So like I mentioned before, where do these products come from? They come from the air that we breathe. So at an ASU, they'll have huge compressors sucking the air out of the atmosphere, and the majority of the power, the biggest cost that's used in an ASU is electricity. So a lot of times the industrial gas suppliers will work out an electrical contract first with the local energy company, and that more than anything else determines where they place the ASUs, because that's probably 60 to 65% of their cost is electricity. You have huge compressors, you suck the air. The air that we're breathing then gets filtered, purified, cleaned up, and goes to the cold box, or it's also known as a distillation column. So what happens in the distillation column is you're zapping it with pressure. All inside here are nothing but trays. You're zapping it with pressure and electricity, and as the gas comes in here, the temperature cools it, cools it, cools it. And if you guys remember, oxygen was the first one based on the temperature to go from a gas. So the first thing that's going to happen is liquid oxygen is going to be made first, and then it's separated and sent to the oxygen trailer or a storage unit. So oxygen will get distilled or made first because of the temperature, and then it's nitrogen, and then it's argon. And argon, if you guys remember, argon was in that 1%. So what they do, they improve the efficiencies of the cold box. They use a lot of the liquid nitrogen to keep cooling it down to get to the argon. So making a lot of argon costs a lot of money. Making a lot of oxygen and nitrogen doesn't cost you as much because it's easier to make when it comes to the temperatures. But nitrogen is overabundant because it's 78% of what they're sucking in, right? So nitrogen is the cheapest out of all the products that are sold in a liquid state. Then oxygen, because it's 21% of what we breathe. 1% is argon and other impurities. That price is much higher, and then it's super expensive for helium and hydrogen. And it's all based on the availability of it and the cost to make it. And the storage tank was 250,000 gallons. So they just stored it. Downstream of that would be where trailers come in and fill and go deliver it. Once you make the capital investment and get this in place and have a really good electric bill with whoever you're working with, it's a cash cow, man. It's a cash cow. It's all about the liquid. Sell the liquid, sell the product, sell the molecule. That's where the money's at. And that's why industrial gas companies are so consistent from year to year and for many years, because it's constant. And I'll get into that a little bit here with the applications, because it is amazing where all this stuff is used, because you just don't think about it, but it's used everywhere. Rego sells direct to a lot of the to the gas producers who do the ASUs, because of the larger valves, and there's more. It's project based, and you know, they're constantly announcing they're going to do ASUs. Just because they announce it doesn't necessarily mean they're actually going to build it. Until they break ground, or have a ribbon cutting ceremony, it's not going to happen. May not happen. Got redundant pictures, but same thing. ASUs are 24/7. Again, if you have a truck, if you're an end user and you have a truck, or you're an independent, your picked up price is much cheaper than a delivered price, which is nice. A lot of the gas producers, I live in Austin, Texas, because when I was working for Air Products, they made me the Motorola account manager when they were making electronic chips, semiconductor chips. We had 11 different fabs there. There were 3 different air separation plants dedicated to Motorola only. So they weren't big, right, relative to a ASU you'll see down the road. But we signed agreements with Motorola directly where we had a superintendent available 24/7, one guy. Whole plant was automated. He would, on weekends, constantly be checking or get notices if something was wrong, have to go out there and fix it. But we had a contract with Motorola, and it was dedicated lock, slin, lar for that chip manufacturing site. So that's called an on-site, because it's specific to a specific customer, right? There are some on-sites by some industrial gas companies where, for instance, in my example, let's say Motorola needed 50 tons a day of nitrogen. They would sometimes cut a deal with the end user and say, hey, I'm going to make this a 200-ton a day plant, and I'm going to guarantee your 50 ton and any growth you have. But if I sell it to somebody else, I'm going to give you 2 or 3 cents per hundred for it. So there are some on-sites out there where they not only they're dedicated to that specific end user, but they're also pulling product for other customers. Motorola wouldn't do that because they weren't comfortable with, they were concerned they get screwed and not have product, so they said no. So in that particular example, they didn't do it. But there are customers who are willing to do that because they can reduce their cost by doing it that way. So sometimes those ASU deals get very creative depending on who they're dealing with and what the market, the immediate market will bear. ASUs make the most sense if you can deliver product within 250 miles or less. So that transport can go to the ASU, pick it up. If he's 250 miles or less, he can drop off product. They try to get the trailers to come back empty. Never want a trailer to come back with any product in it because you're just wasting money. So that's the rationale. Can you get a good sweet deal on the electricity? And if you're going to build an ASU, the capacity of the ASU will be built if they've already sold it and have several pre-contracts set up for at least 60 to 70% because it's a huge capital investment. So the majority of the product has been accounted for, right? But there's always they'll build it a little bit bigger as long as the immediate market has more customers to service or they can steal from a competitor. All right, this has changed over time, but this is just, again, smallest to largest. Packaged gas is just another word for high pressure cylinders or liquid cylinders, small quantities. And then you jump into bulk tanks, small bulk tanks or micro bulks, then bulk tanks. Non-cryogenics, that's the on-site units I was talking about. Or no, I'm sorry, on-site is above it. Non-cryogenics is, there are some pressure swing absorption where they don't liquefy it. They just take the air and filter it, purify it, and then get all the impurities out of there and give somebody just gaseous nitrogen. Those things aren't as efficient. Some of the majors are better at it or not than not. But so that's kind of the supply. And then on the right is basically the family-owned independents usually play in the packaged gas, the lower end of it, because they're selling molecules, but they're also selling hard goods. But those guys have really jumped into Orcas and the micro bulks, and if you're a really good regional player, you get into everything. And then when you get really good and profitable, usually one of the majors will come in and buy you. That happens all the time. Every year there's somebody being bought by somebody for strategic reasons, or they're doing a really good job at what they're doing. Twisco in Houston was a perfect example. Those guys were fun. They bought a shitload of micro bulk, and they basically got out of the hardware stuff and just started. They became a miniature major, is what they became, and they ended up selling because a major finally came in and threw an outrageous number at them. That's the pyramid of supply. What a great title. Here's a supply chain. I'm a visual guy, so you got the ASU plant. That's what's making the liquid, right? If you go on the top, it goes to a trailer. The trailer then delivers it into a bulk tank. Bulk tank delivers it into a liquid cylinder. Liquid cylinder gets delivered to the end user. There's a lot of hands changing in that process, right? You can also have a smaller micro bulk or a truck going to deliver into a permacyl or a micro bulk cylinder, and every combination you can think of in between, right? So liquid's the way to go because of the economics of it. But every time you transfer the product, you're always running the risk of losing the product. Some of it, depending on if you're good at it or not. A lot of the independents will have fill plants or a bulk tank that then, they fill 5 to 20 or how many liquid cylinders at a time. I've even seen some guys use bulk tanks, vaporize it. It's not efficient, but then they fill high pressure cylinders as well. That's not a good scenario. But I just give you a quick visual of where it's made and how it gets to the end user. And then this is just a quick picture of a setup. So the micro bulk or bulk tanks are on the outside of a building, always big white tank. Microbulks are going to be silver. You can put them inside or outside the building. Then you just attach all the piping that you needed. Then you got all the workers who then can use the product. And again, it's like turning on and off a light. It becomes a utility for them. And you can make a delivery while they're working and they don't even know you're there. So where are the products used? These, and this is what's called application. So it is absolutely amazing. You know, the majority of it is welding and metal fabricating, but it is amazing where nitrogen is used for all kinds of different applications and everywhere. And like I said before, the majority of these products are used in a gaseous state. So nitrogen's main function is for blanketing or inerting, heat treating, cool downs, pushing a pig through a pipeline. When I say blanketing or inerting, there's some kind of oven or device that's doing something in the top space they don't want oxygen in, so they douse it constantly or keep that headspace with nitrogen because it's inert and non-flammable. That's what I mean by inerting or blanking. Pushing a pig is when you got to do pipeline maintenance work. A pig is just a circular, it's like a dish or a sphere that they put into a pipeline. They close up the pipeline and they push the dish has sensors on it. And they push it with nitrogen down a pipeline for miles, and it records where there are potential problems with the inner of the pipeline. And then they shut it off, and then they fix the pipeline, then they go down the next miles. So there's rules and regulations on pipelines having to be repaired, and that's how they do it. Reactor cool downs, majority of the it's called nitrogen services, but the industrial gas companies, you got a hydrocracker, hydrotreater at a refinery, huge furnace oven. They used to turn it off and wait 60 days until it cooled down enough to get a live human being in there to then fix the wall, the inner wall of it. The industrial gas companies came in and they have a nitrogen service pumper truck where it's liquid nitrogen. They would introduce and control the temperature with warm nitrogen. So they turn off the furnace or heat treater, hydrocracker at the refinery, and then they introduce warm nitrogen, and then they would control the temperature and slowly reduce the temperature. Within 24 hours, they could get a human being in there to fix what needed to be fixed. Did I say that right? I said that wrong. They put in the cold temperature to cool it down, got the guy in there, or gal, and then when it was all fixed, they then introduced warm nitrogen in there and heated it back up. And those nitrogen service jobs at a reactor cool down, man, $300,000 for rental of the equipment, the labor, and all the product. And the guy would have to be on site the whole time, but they'd knock it out in like 10 days, whereas before it would take 90, 100 days to do it when they didn't control the temperature. And all it was just controlling the temperature up and down within it. And again, this is all in a gaseous state, and the majority of it's gaseous state. Liquid applications, food freezing, flashing, dermatology. So food freezing, your McDonald's hamburgers, Burger King patties. They just take straight liquid with vacuum jacketed piping. Vacuum jacketed piping is just a cryogenic container to keep the liquid in a liquid state. They dump it in a freezer, and the food is on a conveyor belt going this way, a food freezing tunnel. Liquid nitrogen minus 320 instantly freezes it, keeps all the chemistry of that particular product, like Tyson food or a hamburger, and it goes through the tunnel and it's constantly being frozen, and it automatically gets packaged out. Those accounts are phenomenal because they're just using boats of tons and tons of liquid nitrogen. Yep. Flashing is when you're doing like a molding of some sort, like let's say you're putting rubber and you do a mold of a gasket, and they always don't come out clean, so you introduce it to cold nitrogen, and the burring or the the little pieces and parts that are rigid on the side that didn't break off cleanly, the nitrogen will clean it. So once it goes through the cold nitrogen, it comes out perfect. And that's mainly done, that's the theory of flashing. Or they'll dip it in, a lot of times it's like spaghetti. They'll just put it in a big, they'll put all the parts in a strainer, lower the strainer in there, in liquid nitrogen, then take it out, and then they'll break off with a hammer all the parts on that piece that don't make it compliant. So that's nitrogen. Oxygen, again, in a gaseous state, steel, paper bleaching. It's mainly cutting in furnaces are the big ones. Heat treaters. Argon, autoclaves. That's high temperature, high pressure in a device for like sterilizing stuff. Heat treating, metal production. And that's it.